Warning: tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Well, the survey results are in, and the winner is, I think you probably guessed it by looking at the table, 6C33C1. I'm actually kind of glad it did. One, I really wanted to build that other amp, but if I'd have done that first, I may never have come back and done this one. And this is going to be, to me, a lot less complicated amp to build. And so we can probably knock this out pretty quick. Read up on this. I think I have a good handle on like the issues that this little tube has, and what we need to do to make it sing. Part of the magic is this giant output transformer. It's a 600 ohm, 25 watt Edcore. No other people make them, but you guys know I kind of like these Edcore transformers, so decided to get a pair of these for this build. I've had these things sitting here for probably 6 months while I was kind of waiting around to get going on this. So anyway, gonna do this one a little differently than some of the other ones we've done. I know in the past people have been like, where's the BOM? Where's the parts? I can't figure this out. Well, I'm going to show you how I take a schematic that I found on the internet and convert it into an amplifier using parts that are available. And like the schematic that I'm working from used some toroidal transformers. I'm not a big fan of toroidal transformers, so I'm going to show you how to use the PSUD2 software, or how I use it, to simulate some optional power supplies and different ways of getting where we need to be, and just the whole thought process about this part versus that part, and looking up the prices and just figuring out how I'm going to build it. And hopefully that'll be educational and entertaining. So let's break out the software, the parts catalogs, and figure out how we're going to build the power supply for this high-powered singulated amp that we're going to do. And off we go. Okay, so here's the schematic we're going to be working from, and I like this design because, like most of my amps that I build, it's super simple. But I know that these 6C33 tubes are super hard to drive. And so we're going to have a pretty stout driver setup. Now, we'll get into this tube here in a minute. These D3A tubes have become almost unobtainium. And maybe the time when this design was drawn up, they were commonly available. I looked on eBay. They're going for $180, $200 a piece. And I am not going to build an amp that uses driver tubes that are that rare and expensive. So we're going to look up a solution to that. The way they get so much drive out of this single triode strap pentode is using this anode choke or a plate choke. Now this was designed with some transformers that are more common in Europe, which, hey, if you guys want to build it using this stuff, here's the schematic. But I'm going to be using Hammond transformers. And Hammond does make a 200 Henry that has the right DCR and handles 30 milliamps, which will deal with what we're going to be doing for doing a plate choke for this driver tube. You can see here it's running at 20 milliamps. Now, this is more current than I can use with like a 6EJ7, so we're going to have to find a different solution for a replacement for this tube, and I'll show you how I found that. So let's go over this transformer. They're showing they're running at 210 volts at 500 milliamps. Well, they're using one transformer for both channels. We're going to be building it as mono amps, and so we don't need that much current capacity. See here, we're going to be pulling 170 milliamps on this tube, and then this tube's going to be pulling 20 milliamps. So we're going to have a total of 190 milliamps. The other thing to note on this tube is the heater requirements. So we're going to pull up the data sheet, and here's the tube data sheet. As you can see, it's got two separate heaters inside the tube, and you can either run them in series at 12.6 volts, or you can run them in parallel at 6.3 volts. Well, I think it makes a lot more sense to run them in series at higher voltage, because you can see here, then you're only using 2.8 to 3.6 amps instead of this 5.6 or 7.2 amps. And so we need to find a 12 volt transformer that can handle around 4 amps that we can drive the heaters with. The other thing that I've read about these tubes is they have a habit of liking to run away red plate. And people warn about trying to run these as fixed bias, that you definitely can have an issue with the tubes just red plate running away and burning up stuff in your amp. So we're going to be running this as a cathode biased amp, which is what this circuit's doing, and we're actually going to be running it fairly cool compared to what it could potentially deal with. Again, you start running those crazy currents, and then you got to find some insanely large power transformer. But I do want to leave enough headroom in the power transformer so that if we want to play around with running more current through the tube to get more power, that we can do that. So having all of that under consideration and seeing that we're going to be pulling close to 200 milliamps through the power supply, I'm not going to screw around with a tube rectification. I know a lot of my amps run tube rectifiers, but in this case, I just don't think it's a good idea. The other thing that I'm planning on doing is running this power supply as like a two-step warm-up process. I've also read that these tubes like to warm up for 10 or 15 minutes before you actually put the high tension or the high voltage DC to the plate. And so I want to wire this amp up with two power switches. We'll have one power switch that powers up the heaters for the output tube, and then we'll let the output tube get nice and warmed up, and then we'll turn on the high voltage transformer that also has the heater for the driver tube, and then we'll have the high voltage going through the tube and the current running through it and all of that stuff after the tube's nice and warmed up. And since we're going to be operating the power supply like that, there's no point in not just using solid state rectification. There's nothing to be gained from running a tube rectifier. So we're going to be using some sort of transformer here to get the high voltage. I'm not sure whether we're going to run a bridge rectifier or if we're going to run a full wave rectifier. Then we'll be running, a choke here. I don't know if we're going to go all the way to 10 henries. We may run a 5 henry choke and then run a 2 or 3 henry choke after it for the second stage. I think that's plenty of filtration. This seems kind of overkill to me to be running a 10 henry choke and then running a 20 henry choke after it. So the next thing we want to look at is what's available from Hammond. So we go to the Hammond transformer page, and first just look at the chokes and see what kind of chokes we could possibly use in this power supply. And probably going to put one on the top, which would be these enclosed and potted chassis mount. And if we come down here, we have our 193H, which is a 5 henry, 200 milliamp. That's probably a little shy of what we want to be using. 300 milliamps is really overkill. But I'm a little concerned that this 200 milliamp might not be enough. If we go with the strict schematic, it's saying that we're going to be using 190 milliamps, and so this 193H would work, and I actually keep these in stock in my shop. You can see it's a 2.5 pound one. To get up to 300 milliamps, that's a 5.5 pound choke, which is going to be a monster. Yeah, we may end up using that anyway, just to give us some headroom in case we want to try to run some more current through too. So before we make this choice, we probably should run over to the EdCore site and just get into the single-ended tube outputs. Let's find these transformers that I bought. And primary impedance is 600 ohms. It's the only one they make. It's a 25 watt, 600 ohm, single-ended transformer. And you can see here it's got a screen tap, so we can wire it up as an ultralinear style transformer. And the maximum current is 250 milliamps. So that would be the top end of what we could do. And go back over here to the choke. Yeah, we're going to have to go with this 300 milliamp choke if we really want to push this tube. And that's safer than trying to go with this 200 milliamp one. So we've got that choke. We're also going to need a smaller one like this. And let's see what they have in 300 milliamps. You can see we're kind of running out of options here. There's a 200 milliamp. There's a 225. We might be able to get away with that, but here's a 2.5 Henry at 300 milliamps, which is probably more like what we want to be using. And that's still going to give us some nice filtration, and it matches what that big choke on the top is going to be. So make a note of that, a 159T. Then we'll go back here and look at the power transformers. Whoops. And there's the power transformers. And I'm showing you all this just to kind of give you an idea of when people say, oh yeah, can you whip up a bomb for this? It's like coming up with all these part numbers for even just the iron is just a very time-consuming process. So let's see if there's anything in this 200 series, which are usually more reasonably priced. And you can see they do have a 200 volt secondary that's 250 milliamps, and it's also got a 6.3 volt tap to use for the driver tube. We don't need this 5 volt because we're not going to have a tube rectifier. So this transformer right here might work well if we are using a bridge rectifier. And it doesn't look like this thing is a giant monster of a transformer either. And again, there's no point in going over 250 milliamps because the output transformers can't go over 250 milliamps. Now, another option would be if we went with a full wave rectifier, and we would probably need something around 500 volts to get the B plus voltage that we need. And again, I need to do some calculations in the software that I have to see if 200 volts into a bridge rectifier will get us where we want to be on our plate voltage. But if we look down here in this series, they're getting up here to 550 volts before you get up over 200 milliamps. And while this one's really close, I just think 550 volts is going to get us over the plate voltage we want. And it's got taps that we don't need. We don't need 6 amps. So this one probably is going to be at a good price point and is going to do what we need to do. But I need to do a little simulation work and see. So let's look in this 300 series. And these are the kind that also work in other voltages besides the US. So that other transformer would only work on 120 volts. And these will work on 120 or 240. So come down here and look. Okay, they've got a 500 volt, 322 milliamp. Probably going to be a beast of a transformer. Now here we've got 450 volts, and they've got both a 150 milliamp and a 300 milliamp. I don't think this 150 milliamp is really going to work for what we're wanting to do. It's got the volt amps. If you're not using this tap, and we're not using the 6 amps, but I still think this is kind of pushing the envelope on what this can do, and I like oversizing the transformers. And so this 450 volt center tapped 300 amp transformer might be an option if you're living in countries that don't have 120 volts and you need this 300 series transformer, and it could be wired up as a full wave rectifier. So we've got 2 options on our power transformer here. So let's jump over to the power supply simulation software and see what we can cook up that'll hit the voltage that we want to see on our plate. Okay, so we pulled up this PSUD software, and I'll put the link in the description below. And I've configured this for a potential power supply layout for this amp. So in this window here, I set it up for a full wave solid state rectifier. And here we have a 22 UF. I really like these Soling caps that I've been using in a lot of my amps. And we can play around with this value, and I can show you what that does in a minute. So here's the choke we picked out. It's a 5 Henry, and it's got 57 ohms of DC resistance. I have a 100 UF cap following that. Then we have a 2.5 Henry. These were both 300 milliamps, and so was the transformer. And this one has 43 ohms of DC resistance, and have a 100 UF cap here. And then we have our, actually this is 190 milliamps. And then we will simulate the results here. And this is voltage here. And we're seeing 257 volts at this 190 milliamp load. And if you remember on our diagram, we had 255 volts we were looking for. So we're spot on the voltage that we want to see here. And we can easily drop this down to this 250 by using a resistor capacitor decoupling little network that we're going to have to put in here anyway. Now see, they're using a choke cap. We're going to use a cap, choke, and then go to the output transformer. So we're going to put an extra stage of filtering going to the output transformer, and then we're going to put a resistor cap decoupling filter to go to the driver power supply, or going to this choke that's feeding this front end tube. So this looks like a viable setup, and this is using that 450 volt 300 milliamp transformer that we found on Hammond's website, which was this one right here, this 369KX. So back to our software, if we change this to 33 UF, let's see what that does to our voltage. Because sometimes it'll make a difference, and sometimes you kind of get at a point where it doesn't. And that gets us a few more volts here. So if we end up needing a little more or a little less plate voltage, we can play with the size of this capacitor here. That's the first reservoir capacitor in the power supply to get us where we want to be. And if you look at the voltage here, look how zero ripple this thing has. I mean, we're going out to 3 decimal points, actually 4 decimal points. So this is going to be a super clean power supply if we build it like this. Now the other option that I want to play with is we're looking at that other transformer that was using a bridge rectifier, and it was 200 volts. And let's see what kind of voltage we're going to get out of this. Yeah, see, it's not going to get us there. That's 226 volts. Before we just say that's not going to work, let's try raising this up to 100 microfarad and see what that does. Yeah, that got us up to 230, but that's really not going to get us where we want to be. Now let's look at the DC resistance of the windings on this guy and see, it was this guy right here, 200 volts. So if you open up this PDF, it'll show you here, it's actually 24.9 ohms of resistance in the transformer. And let's see what that does to our calculation here. So it was right at 25 ohms. Let's see if that changes anything. That gets us up to 235. Still not really where we need to be. Now if we look at the voltage up here at C2, we've got 244 volts. We're losing 10 volts across this. So if we take this out, that gets us up to 244 volts using a single choke. And you can see this is still a fairly clean power supply. We're 2 digits out on the ripple. So this could be an option. It's going to have the plate voltage a little lower than what we really want to see. We'd be about 10 volts low. But I'm going to have to run the pricing on that too. I might be willing to give up 10 volts of plate voltage to build a cheaper version of this thing and not have to buy as expensive of transformers. So let's look at that real quick and see what the pricing is on these 2 different transformers. One is this 269AAX. So let's just do a quick Google search on that. And I've been buying a lot of stuff from Hawk. Wow, that transformer is only $72. I mean, that's a good deal. I have a feeling that other one's going to be exponentially more expensive. This 369KX. Let's see what that comes up with. Yeah, it's twice as expensive. So, for you guys over in Europe, this is the only option if you're going to go this Hammond route. But I'm almost thinking for what I'm doing, to try to save some money, is go with this 269AAX. And the other thing that you can do with these, because like we are looking at being a little shy on the plate voltage, they have a 115 and a 125 volt primary. If you need to get a little more voltage out of it, in my house the voltage is right at 122 volts. And so if I use this 115 volt tap, that'll cheat a little more voltage out of the secondary. And again, there's no point in going over 250 milliamps, because the output transformers are only rated for that. And there's no point in having the 5-volt rectifier windings because we're not going to use those. And this will easily power up the single driver tube we have. So I think I'm going to do that. I think I'm going to build it with this simple single choke, put 100 UF cap. I mean, I might even, let's see if this helps. Let's go up to a 220 UF here and see if that cleans up some of this ripple. Oh yeah, that cut the ripple in half. Let's just have some fun here and see what a 470 does. And see, that's the cool thing with the software is you don't have to build it and measure it. You can just play around with the numbers in here until you get the power supply where you want to see it. See, the other thing that I'm not used to dealing with is with a solid state power supply, especially if we use a really beefy bridge rectifier, we can use some pretty big caps here. You don't have to worry about blowing up stuff like you do with a tube rectifier. And using a 220 UF and then a 470 UF, we're getting out to 3 digits again with the ripple. I think this is what we're going to go with. I'm going to go with this 200 volt. I'm going to get a nice one-piece bridge rectifier. I mean, this is calculating with 1N 407s, but we can find some, fast switching bridge rectifier that's all in one case, and then use a 220 UF and a 470 UF, and using the white and gray ones instead of the white and black, we should be able to get another 10 volts out of the power supply. And these are only $70 a piece. The last thing I want to do is see how expensive that choke is. I don't think they're going to be really bad. So let's go back here to the chokes. And it was the 193L. I mean, we probably could get away with this 193H. And I've got these here and not have to go out and buy chokes. And we're only at 190 milliamps if we build it like the schematic showing. And then later on, if we did decide we wanted to push the tube harder, we could swap out to these 193Ls. Let me just see how expensive these are. Okay, these are $80 for that choke. And then let's see what a 193H is, just in comparison. Yeah, see, these are only $45 versus $80. And you got to remember, we're doubling this. We're having to build 2 amps. And so, that's 80 goes to 160. And then the transformer, if it's 144, that's $300 for power transformers versus 150. So, yeah, I think we're going to try these 193Hs. And the last thing I just want to make sure of is how much more resistance does it have? Yeah, it's only got a few more ohms of resistance, so I don't think it's going to be a problem. And it's a lot smaller choke too. See how this is, 2.5 pounds instead of a 5.5 pound choke? It'll make the chassis and the whole amp a lot more compact to go with this. So I think that's how we're going to do the power supply. Unfortunately, if you're in Europe, you guys are going to have to go with that one that I showed earlier that's got the full wave, or you could get a toroidal. I'm not a big fan of toroidal transformers. I've seen issues with them blowing fuses and just doing weird stuff. They're just, I don't know. I really just like EI core transformers better. So I'll have to go to Mauser, try to figure out what kind of bridge rectifier we want to use, and then we'll have the power supply design. Well, I think this is a good place to wrap up this first segment of this project. And I know it may have seemed like I was jumping back and forth and all over the place, but that's kind of what this process is like. When you first start out, you go, hey, this looks like it'll work. But wait, there's more. And we could come back and figure out a different way of doing it. And then we go look at the parts prices and we go, hey, I don't know, that's going to cost 3 times as much to do it this way. And while this way might be, you know, closer to the edge and not just like a super overkill build, it's going to work. And it's half the price. And unfortunately for you guys in Europe, you're not going to have the option of using these 2 series transformers because they're 115, 125 volt only. So you're going to have to use that 3 series and, you know, deal with the full wave rectifier deal, maybe using some different parts inside it. You guys can figure that out because now you know how to work that PSUD2 software. There's likely some manufacturers over in Europe. I may actually look and see what Thermionic Labs has and see if they possibly have some power transformers that are made for this, or maybe even talk to them and see if they'll wind up something like that 200 series Hammond transformer at 200 volts with 250 milliamps, so you can just drop in one that's at the 230, 240 volt that you guys need. So anyway, I looked up the sizes of that 200 series Hammond transformer, and believe it or not, it's about the size of this choke. And so this is the plate choke, this is the power choke, and then the power transformer is going to be almost the same size. One of the things I do know is this tube is a little heater. I mean, it puts out a ton of heat. So I want to come up with a chassis size where this thing is, you know, a nice distance between it and this iron, so it doesn't just cook this transformer. And then we probably want to put the driver tube, you know, like over here, pretty far away from it as well. I've heard these things get so hot that you really should mount the tube socket on spacers on top of the chassis so that air can circulate underneath the tube socket. So we're probably going to be doing that in this build as well. So the next video we will look at figuring out how to do some of the other parts from the power supply and figuring out the chassis that we're going to use. I know you guys said you wanted to see a wood chassis. I think for this build I'm going to use a steel Hammond chassis, a pair of them, just trying to keep this thing on a budget. And we'll do the 4E27 amp as more of a high-end build with a wood chassis because we're using ISO Tango transformers and all that kind of stuff. And we'll do this 6C33C as a budget build. You can use cheaper tubes and just all that stuff and try to make this as low cost as possible so we can have like a low cost kind of crazy powered one, and then we can have the high cost one, which I think makes sense. So anyway, hope you're enjoying this content. I'm really excited about getting these amps built, and like I said, I think I can knock this one out pretty quick. Hopefully I can get some power transformers here and the other few parts and the chassis and get to building these things. I want to thank you folks that participated in the survey and let me know what you want to see built next on the channel. And somebody made the comment, where are the KT88 monoblocks? If you remember, I said that they would be coming this summer. So I haven't forgot about them. And they're not like totally on the back burner, but I wanted to knock out some kind of unique content that KT88 monoblock is honestly going to be a lot like my KT120 build with just smaller iron. It's basically going to be the same circuit. So if somebody wanted to jump ahead and build those, just copy that circuit that I did with my KT120 monoblocks and use the software that I just showed you how to figure out like what transformer to use, and you know, a smaller output transformer, you know, you probably get away with a 15 or 20 watt ones. 20 is probably a good size to go for, and just build them like that. So anyway, till the next video, have a nice day.